Bismillahirrahmanirrahim. So let's look at some examples, few examples. Here it says that closed rigid tank consists of 1 kg of air at 300 Kelvin. So state 1, we have temperature of 300 Kelvin. Our system consists of 1 kilogram of air and it's rigid tank. Okay, rigid tank means that the volume is constant, so V equal constant. The air is heated until its temperature becomes 1500 Kelvin. So state 2, we know that the temperature at that state is 1500 Kelvin. Neglecting changes in kinetic energy and potential energy and modeling air as an ideal gas, determine the heat transfer Q in kilojoule during the process of air. So we have this. If we want to draw it in TV diagram, then state 1 will be at a certain pressure and temperature of 300. Since this is closed system, then when the temperature increases, then of course we'll expect that the pressure will increase, and that's what the constant pressure lines also indicate, because if this is the temperature, then our process, okay, if this is the temperature, then this is the pressure, and the process goes vertically up because this is constant volume, rigid tank. This is something very important to notice. Okay, you will not be told, or I mean this example, you are not told that the volume is constant, but you are told that it's a closed rigid tank. Then you should understand, okay, that means that the volume is constant, and therefore, since it is closed system, the mass is also constant, the volume constant, therefore the specific volume, which is the volume divided by mass, will be also constant. So these things that you need to notice and use, because as we'll see, this is an important thing to know. So now, if we apply the energy balance equation, then Q minus W equal the change in the system energy, and the change in the system energy composed of the change in the kinetic, potential, and the energy. We are told that the kinetic and the potential energy are 0. We are told the system is rigid, and there is no work, there is no shaft work, there is no electrical work. Therefore, the work also is 0. Then we have delta U equal Q, and the total internal energy equal the mass times specific internal energy. So we need to find what is U2 and U1. We are told that we can use, we assume air as ideal gas, so we can go to table A22, which is ideal gas properties of air. We have the temperatures T1 300 and T2 500. Then this here is 300, and that will give us U, and this here is 500, and this is the value of U. So we simply substitute here. We have the mass as 1 kilogram, and we can find this in kilojoule. So straightforward, almost. And then in this problem we have piston cylinder assembly contains 2 kg of water. Again, this is closed system, but now it's a piston cylinder, so the volume is not constant because the piston will move. So you have 2 kg of water vapor. So this is vapor at 100 degrees Celsius and 1 bar. The water vapor is compressed to a saturated vapor. Okay, so state 2 is saturated vapor. Okay, at a pressure of 2.5 bar. During the compression, there is heat transfer of energy from the water to the surrounding. So there is heat transfer out. That's why the heat here is negative, because it's out of the system. So here says the heat transfer from the water to the surrounding, and the magnitude is 250. So it's your job to know that this is a negative, because the system is losing this heat. Again, we neglect changes in the kinetic and potential energy. We need the work in kg of the process. So if you want to draw this, let's say that we need to draw that in TV diagram. Here we should know how the constant pressure line. So this is constant pressure line of 1 bar, for example. You will see that the saturation temperature is 99 point something. Okay, I'm not sure, but it is less than 100. Therefore, point 1 is somewhere here, state 1. Then state 2 is P2 equal or in saturated vapor with the higher pressure. So the higher pressure means that the pressure line is above P1. So it will look like that. Then the process goes from 1 to the saturation. Okay, so this is 2, and this is the line showing the process. Okay. So again, we apply the energy equation, the kinetic and the potential, the change in the kinetic and the change in the potential energy, 0. Then we have work equal Q minus this. Okay, just simple simplification of that. Please remember, this is the interior energy, and these are the specific interior energy that we get from the table. Now we go to the superheated table with temperature of 100, the superheated table of 1 bar, and we look for temperature of 100, and that will find that this equal to this. Let me try to here. So 1 bar, this is 1 bar, and this is 100. Okay, so the interior energy is this value, 250.6.7. Okay. Then state 2 is saturated vapor. So we go to the pressure saturated vapor, and we look for 2.5 bar, which is table A3, and there we know that this is saturated vapor, so we take UG and we find this, and then we simply substitute in the equation that we have with the correct sign of the heat transfer, and that will be our solution. Okay, the negative sign indicate that the work is done by the system. Okay, is done on the system. Okay, so we have compression. So something is compressing the piston, so the work done is on the system. That's why it is negative. In this example, we have well-insulated rigid tank having volume of, so we have the volume, and again, this is a rigid tank. So what does that mean? That the volume is constant. Okay, contains saturated water vapor. So we have a saturated water vapor, and then we have sealing. So we have shaft work input until the pressure increased to 1.5 bar. We need to know the temperature at the final state and the work done. So so what we have, we start, neglect this, okay? So this is the TV diagram. We start at saturated vapor. Since this is rigid body, then the volume is constant, okay? And so this is pressure of P1, and P2 equals 1.5 bar, okay? So state 2 will be here, and it will be superheated. So what do we have here? Okay, in state 1, in state 1, we know that T1 equals 100 degrees Celsius, and this is saturated vapor. So we go to the saturated vapor table A2, and we find what is Vg, okay, at 100 degrees Celsius. This is the saturated vapor. This here is Vg, and that's 100 degrees Celsius. Then what do we know in state 2? In state 2, we know that the pressure equals 1.5 bar, and we know that V equal Vg. So we have two properties, two intensive and independent properties. Then it means that from these two properties we can know what is T2. This is P2 and P2. Let's try to do that. So we go to the table A2, and at temperature of 100, this is temperature of 100, okay? This is the saturation pressure, this is the VF, and that's Vg. So Vg is 1.673, okay? So this one here, Vg equal 1.673 cubic meter per kilogram. Now we use this, and so we know what is V2, and this equals V2 since it's constant volume. We know the pressure is 1.5 bar. We know that state 2 is superheated. Then we go to the superheated table, and superheated table, yeah, yes, this one, and we look for pressure of 1.5 bar, which is this one, 1.5 bar, and 1.673. So specific volume is 1.673, which is between these two. Okay, so this is 1.5 bar, and this is between these two. Okay, and then we'll have two values, T A and TB, and here we have two values. Let me okay, so our value 1.673 is between these two values of the specific volume, and so our temperature will be here. This will be T2, and you know what you should do now. You should do interpolation. Okay, so this is V, and this is T, and then you will this is T1 or 240, and this is 280, and then this is 1.57, and that's 1.695. and this is 1.673, and then you need to find T2. Okay, so that's how you should do it. And you can look at this example in the book. Here we have piston cylinder assembly. We have the mass. We have initially we have saturated vapor. So state 1 is saturated vapor. We have constant pressure. Okay, and the pressure is 1.5 bar. So we know that it's 1.5 bar. State 1, 1.5 bar. Saturated vapor. So we can go to table A3 and find all properties of state 1. Then there is heating, expand at constant pressure until the final temperature is 25 degrees Celsius. Show the initial and final in TV and PV diagrams, and determine the volume at the end and the work during the process. So this is pressure of 1 bar, and we start with the saturated vapor. Then this is Vg is known, therefore V1 equals Vg times m, times the mass. Now the TV diagram, okay, we are told it's constant pressure. This is constant pressure line, and the process says it starts. State 1 is saturated vapor, okay, and then temperature increase, but constant pressure. So this is state 1 here, and state 2 there, and this is pressure of 1.5 bar. For PV diagram, okay, we have, this is state 1, saturated vapor. This is constant temperature, but the process is with constant pressure, pressure, yes. So this is state 1, this is state 2, and we'll have something like that. This here, the line of temperature of 25 degrees Celsius. So we know that pressure is constant, therefore it's 1.5 bar. We know that the final temperature is 25. Then this is the final temperature, and these are all the properties, and this is V2. And again, the final volume equals V2 times m, the same mass. Okay. Regarding work, we know that Q minus W equals delta U. The kinetic and the potential energy are not there. From the table, we know this is U1 because it's UG. U1 equal UG, and this is U2. Okay, so delta U equals m, U2 minus U1. Okay, the volume is occupied here. We know that during this process the piston will move at a constant pressure, therefore the works is simply the pressure times V2 minus V1. So we found what is V2, we found what is V1, we know that the pressure is 1.5 bar or 150 kilopascal, then this can be known. From here, we can know what is the heat transfer. Okay, and I think I will leave this example to you so that these are in the book. There are very good examples. Please look at them and learn how to draw the processes in TV and PV diagram. And as I told you, to do that you need to know the behavior of constant pressure line and the constant temperature line. Thank you, and by that we are done with the chapter. I hope that you understood it.